Hi, you might recall earlier this unit we talked about a French mathematician named Clairaut, and one of his theorems that he worked on with multivariables said that if we were to take multiple partial derivatives, the order in which we take them does not matter. We call this implied commutativity. That means it's implied that we can order the way we order our partials is irrelevant to the answer, given that the function is continuous, and that's a big word right there. It has to be continuous, and that's the word that we talked about last year in calculus. So let's see here. So we're given this function f of x, y, z as e to the negative x sine y, z, and we asked to show that all of these partials are indeed equal to each other. And this isn't very fun, but one thing I want you to notice is that when we're taking the derivatives, it's the partial of x, y, 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 x, y, 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 x. What I want you to notice is that they're all the same number of y, same number of partials with respect to x. So let's take a look at the first one. We want to take the partial with respect to x. Now this sine of yz is on the inside. So if I take the derivative, is my constant, So if we take the derivative, we're going to get negative e to the negative x times the sine of yz. And if we now take that derivative with respect to y, well, y is on the inside, so we have a chain rule. This becomes negative e to the negative x times, well, the derivative sign is cosine of yz, and we're going to multiply that by the derivative of the inside, which is just z. And then we're going to take the derivative of this one more time with respect to y. Again, this time the e to the negative x and z are my constants, so I can just place those together. E to the negative x times z. The derivative of cosine, because my y is on the inside, becomes negative sine, so it becomes positive. So I get sine of yz. And again, I'm going to multiply by the derivative of the inside, and that's going to give me z squared right there. All right, so we got the first one. Now we want to try the partial of y, x, y. So let's find the partial with respect to y. Again, y is on the inside, so I have to use my chain rule. The e to the negative x is just a constant, so that's e to the negative x times the derivative. We're going to get cosine of yz times the derivative of the inside, which is just z. And now we're going to take that derivative with respect to x. Now in this case right here, all of these are my constants. So when I take the derivative of e to the negative x, that's going to become negative e to the negative x. And I can bring that z to the front, because it's just a constant. That's going to give me cosine of yz. Whoops, that should be yx right there. And now I'm going to take the derivative with respect to y again, yxy. Like when I broke up with somebody, when she broke up with me, poor Amanda, yxy. Alright, that was dumb. Alright, so when I take the derivative, again I'm taking the derivative, there's my y right there, it's inside. So I do have a chain rule. This is all a constant, so I can just leave all of that alone. And we get the derivative of cosine is negative sine, becomes positive, and we're going to get sine yz, but again, take the derivative of the inside, and that becomes z squared. And right away, you can see that they're already the same here. And now we look at the last one, yx. So if we take the partial with respect to y, and we take this derivative with respect to y, again, this e to the negative x is my constant, so that becomes e to the negative x. Y is at the inside, so we're going to get cosine of yz times z. Again, it's just going to look just like this one. It's the same partial. But now I'm going to take the derivative with respect to y again. Now again, this z is a constant, so it's e to the negative x. So I'm going to bring those together, times z. Take the derivative of y. It's inside, so I've got to use my chain rule. We get negative sine yz times, and again, take the derivative of the inside, that's my quotient, that's my chain rule, z, so I get z squared. And now my last one is take this derivative now with respect to x. So again, this z squared sine of yz are a constant, so we're going to leave those alone. And when we take the derivative of e to the negative x, that becomes negative e to the negative x, making that positive e to the negative x. And indeed, they are all the same. Basically what they're saying here is the order in which we take those derivatives shouldn't matter. We can arrange them any way we want. And in some cases that does make it easier for us. So let's look at the next problem. We want to find the partial derivative of this function xy, x squared plus cosine e to the y plus y squared. But we want to take them in the order, the partial with respect to x, y, x, y, x, y. Well, if I take the derivative of e to the y, that is a lot of chain rules. And that can get very messy right there. So another way if I can arrange it, I notice this x squared here. I notice that the power on x is 2. Well, last year in calculus, we talked about something called the derivative annihilator. And that says that the third derivative with respect to x, with respect to x, is going to be 0. Therefore, it'll be annihilated. That is what we call the derivative annihilator. So you need to look that up. Go ahead. It's a really cool phrase. You have been annihilated. So since I recognize this as a derivative annihilator, I look over here. Well, notice I'm taking the derivative with respect to x 3 times. So I can say that the partial derivative with respect to xy, xy, xy is the same as if I took all the partials with respect to x first. Y, y, y. They're going to be the same. That's what Clairauts' theorem says. So if I take the derivative now with respect to x, that's going to give me 2x. This whole cosine is just a constant, so I can just leave it alone. The second derivative with respect to x becomes 2 cosine e to the y plus y squared. And if we take the next derivative with respect to x, notice the derivative 2 is just 0. So it doesn't matter what this is. So the third derivative is 0. And therefore we can say that the derivative of x, with partial derivatives with respect to x, y, x, y, x, y, is also going to equal 0 as well. So let's see another one here. Now, so here we have a function f of x, y, x cubed y squared minus y over x plus the natural log of x. And we want to find the partials with respect to x, 3 x's and 2 y's. Now the problem is if I look at the derivative with respect to x, that gets really complicated. This is more complicated with the x's on bottom. So what I might want to do is, well, the derivatives with respect to y is a lot easier. So therefore, I'm going to take the derivatives with respect to y first. And there's also something else I know. When I'm looking at the derivatives here, if I ignore this one's easy either way, x or y. But it's this one. If I take the derivative with respect to x, that's like saying we have a function f of x equals 1 over x. The derivative is slightly more complicated. I mean, it's not bad, we can do it, but we would have a chain rule right here, which makes it even worse. So if I take the derivative of something like 1 over x plus natural log of x, we're going to get negative 1 over x plus natural log of x squared times 1 plus 1 over x. Well, that would just be the first derivative with respect to x. Then we got to do the second derivative, which becomes quotient rule. But if I treat x as like a constant and looking only at the y's, this is like saying y over 5, well, its derivative is just 1 over 5. So I notice that's going to be a lot easier to do. And that's why I'm going to take the derivative with respect to y first. So when we take this derivative with respect to y, we would fy would equal 2x cubed y minus, now remember, this is y over a constant. So that just becomes 1 over x plus the natural log of x. Oh, that's nice. See, I already got rid of that. Now, and take a look at this is all in terms of just x. And if I take the second derivative with respect to y, So if I do my y's first, basically, I'm going to get 2x cubed, because there's a 1 that drops down, minus, well, there are no more y's here. That just goes away entirely. So I don't even have to worry about it. So therefore, we can say the derivative of x, the partials with respect to x, and then 2y's, is just going to be 2. Oops, not done yet. Messed up there. Hurry. So we got the y's first. Now, we're not done because we still have our x's. Excuse me. So I got a little ambitious there. Sorry about that. So now we can take the derivatives with respect to our x's. Well, I need 3x's, so the derivative here with respect to x is just going to become 6x squared. The derivative with respect to x one more time becomes 12x. And now there's one more x we have to take the derivative with respect to. And that just becomes 12. And there is our derivative. Sorry about that. I got a little carried away with myself. I forgot we had to take the derivative with respect to x's. Just because you change the order doesn't mean you can eliminate variables there. So be careful with that. All right, go to part 2. We'll take a look at a few more examples that we see these in physics.